Now let us discuss about electromagnetic induction. We will have a first hand look about introduction on electromagnetic induction, followed by important points about Faraday's law, Lenz's law, motional EMF, power, mutual inductance, self-inductance and AC generator. This will be followed by practice questions. Introduction. The phenomenon in which electric current is generated by varying magnetic field is called electromagnetic induction. Here magnetic flux is given by pi of B is equal to B into A into cos theta, where B stands for magnetic field, A stands for area vector and theta stands for angle between the magnetic field and area vector. The SI unit of magnetic flux is Tesla meter square, which is a scalar quantity. Now let us have a look at Faraday's law of electromagnetic induction. The magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. That is, induced EMF is given by minus d pi b by dt. Here the negative sign indicates the direction of induced EMF and hence the direction of current in a closed loop. For a coil with n turns, this induced EMF is equal to minus n into d pi b by dt. Induced EMF can be increased by increasing the number of turns of a closed coil. Now let us understand Lenz's law. As per Lenz's law, the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Motional EMF can be given by the formula EMF equal to B into L into V, where B is the magnetic field and V is the velocity of the conductor and L is the dimension that remains constant throughout the motion. Power required for motion, this is given by P is equal to B square L square V square by R, where R is the resistance of the moving conductor. This power is dissipated as heat. Charge flow and change in magnetic flux. Delta Q is given by delta pi B by R, that is change in magnetic flux divided by the resistance of the moving conductor. Changing magnetic fields can set up current loop in nearby metal bodies. They dissipate electrical energy as heat. Such currents are called as eddy currents. Now let us understand inductance. This is very important from examination point of view. An electric current can be induced in a coil by flux change produced by another coil in its vicinity, or by flux change produced by the same coil. Flux through a coil is directly proportional to the current. Inductance can be given by general formula N pi B equal to K into I, where K stands for inductance. There are two types of inductance. One is mutual inductance and another one is self-inductance. Mutual inductance of a solenoid S1 with respect to solenoid S2 is equal to mutual inductance of solenoid S2 with respect to solenoid S1. That is, mutual inductance in solenoid S1 due to the presence of solenoid S2 is equal to mutual inductance at solenoid S2 due to the solenoid S1. Both are equal. This mutual inductance can be given by the formula mu naught into N1 N2 into pi R1 square L. The EMF induced here is equal to minus M di2 by dt. Here M stands for mutual inductance and I2 stands for current in the solenoid S2. You can notice that this epsilon 1 or EMF in solenoid S1 is equal to or is directly proportional to the current in solenoid 2. Now let us understand self-inductance. The EMF induced in a single isolated coil due to change in flux through the coil by means of varying the current through the same coil. Here the self-inductance is valid for single isolated coil. However, mutual inductance is valid for two coils placed closer to each other. In case of self-inductance, the formula is N pi B equal to L into I, where L stands for self-inductance. In self-inductance, the energy required to build up current I is equal to L I square by 2. Now let us understand important formulas in AC generator. Here instantaneous value of EMF is given by NBA omega sin omega t, where N stands for number of turns, B stands for magnetic field and A is the area vector. Also EMF can be given by epsilon naught sin 2 pi mu t, where omega equal to 2 pi mu. Now let us get on with practice questions. Question number 1. A rectangular wire loop of sides 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 cm per second in a direction normal to the longer side and also in the direction normal to the shorter side of the loop. Also find out for how long does the induced voltage last in each case. Here let us understand this question clearly. Here the given rectangular loop, it moves in a uniform magnetic field and we need to find the EMF developed across the cut if the velocity is normal to the longer side. That is, the velocity is perpendicular to the longer side of this rectangular loop. And also in another case we need to find the EMF if the velocity is perpendicular to the shorter side of the loop. That is to the least dimension of this rectangular loop. Also we need to find for how long this induced voltage will last. Now in first case, calculate area of the loop. Now area of the loop is 16 centimeter square. Here B is given as 0.3 Tesla and velocity as 1 centimeter per second. Now let us first calculate the EMF developed if the velocity is normal to the longer side. This EMF is equal to magnetic field into length of the coil, which is stationary or which will not change during motion, and V velocity. So 0.3 into 8 into 10 power minus 2 into 10 power minus 2, that gives us 2.4 into 10 power minus 4 volt. Time of lasting in this case is given by time equal to distance by velocity, which is 2 seconds. That is the EMF developed when velocity is normal to the longer side. It lasts only for 2 seconds. Now in case 2, let us find out the EMF developed if velocity is normal to the shorter side. In this case again we are using the same formula BLV. However, here the constant dimension or the dimension that does not change with time is 2 into 10 power minus 2 meter. Thus the induced EMF is 0.6 into 10 power minus 4 volt. And time of lasting is distance by velocity, which is 8 seconds. Question number 2. Current in the circuit falls from 5 amp to 0 amp in 0.1 second. If an average EMF of 200 volt induced, give an estimate of the self-inductance of the circuit. That is, the change in current is given and also the time period within which the change has happened in current is also given, and average EMF is 200 volt. We need to find out the self-inductance of the circuit. Here we know the EMF generated due to self-inductance E is equal to minus L di by dt. di is nothing but the change in current with respect to time. Thus di is 0 minus 5 and dt is 0.1 seconds. On calculation we get L equal to 4 Henry. Question number 3. Is principle of relativity relevant for Faraday's law? If so, give reasons. The answer is, an EMF is induced in case of moving charges as per Lorentz force. However, even if the charges are stationary, an EMF is induced in the presence of varying magnetic field. Thus, moving charges in static field and static charges in varying field seem to be symmetric situation for Faraday's law. Thus, principle of relativity is relevant for Faraday's law. Question number 4. A jet plane is traveling towards west at a speed of 1800 km per hour. What is the voltage difference between the ends of the wing having a span of 25 meters? If the Earth's magnetic field at the location has a magnitude of 5 into 10 power minus 4 Tesla and the dip angle is 30 degree. The answer is, Earth's magnetic field at a place will have two components, BH and BV. That is, the field along the horizontal direction and field along the vertical direction. It is the vertical component that develops an EMF across the wing in north-south direction. Thus, EMF is given by BV into V into L. BV stands for the magnetic field in vertical direction. V is the velocity and L is the length of the wing or wingspan. So, BV can be calculated by the formula B sin D. This is from simple trigonometry. Thus, we get EMF induced equal to 3.125 volt. Question number 5. Two identical loops, one of copper and other of aluminum, are rotated with the same angular speed in the same magnetic field. Compare the induced EMF and current produced in the two coils. Justify your answer. Let us first compare the induced EMF. Induced EMF is given by the formula BA omega sin omega t. This formula you might have noticed in AC generator. Since both the coils are identical, it will have equal area. Also, magnetic field and angular speed are same as per the given data. Hence, induced EMF in both the coils will be the same. Now, let us understand the current produced in the coils. The current is given by V by R. Here, only differentiator between copper and aluminum is resistance. Copper has least resistance compared to aluminum. Thus, current produced in copper is higher than that in aluminum coil. Question number 6. An air-cored solenoid with length 30 cm, area of cross section 25 cm square and number of turns 500 carries a current of 2.5 amps. The current is switched off in a brief time of 10 power minus 3 seconds. how much is the average back EMF induced across the ends of the open switch in the circuit. Ignore the variation in magnetic field near the ends of the solenoid. The answer is average back EMF can be given as the difference in the flux divided by time. That is final flux minus initial flux divided by time. We know final flux is 0 because the current is switched off, and initial flux is given by the formula NBA. So the initial flux is calculated as 6.54 into 10 power minus 3 Weber. On substituting this value to average back EMF formula, we get average back EMF equal to 6.54 volt. A circular coil of radius 8 cm and 20 turns is rotated about its vertical diameter with an angular speed of 50 radian per second. In a uniform horizontal magnetic field of magnitude 3 into 10 power minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. If the coil forms a closed loop of resistance 10 ohms, calculate the maximum value of current in the coil. Also calculate the average power loss due to Joule heating and explain where does this power come from. We know by Ohm's law maximum value of current is equal to maximum EMF induced divided by resistance. Also we know the EMF formula is BA omega sin omega t. This EMF will be maximum if sin omega t equal to sin 90 degree. Thus sin omega t can be taken as 1. Thus maximum EMF is given by BA omega. On calculation we get maximum EMF equal to 0.603 volt. And maximum value of current is maximum EMF by resistance. Thus BA omega by 10. This gives us the maximum value of current equal to 0.0603 amps. The formula for average power loss is 1 by 2 into maximum EMF into maximum current. Thus half into 0.603 into 0.0603. On calculation we get average power loss equal to 0.018 watts. And the source of power, it will be from the work done in rotating the coil. That is, when we rotate this coil, a work is being done. This work is the source of this power.